Today we're looking at transformations that are not rigid like the ones we looked at yesterday. So these are going to be our stretches and compressions. So what we are transforming today is going to keep the same shape, but it's not going to keep the same size this time. So our first kind is vertically stretching and shrinking our graphs. So if f is your function and c is a positive real number, if c is greater than 1, then the graph of y equals c times f of x is the graph of y equals f of x vertically stretched by multiplying each of its y coordinates by c. So the picture here on the left would show us that one. Our graph of f of x is the blue one here. And then if c is greater than 1, then it stretches the graph vertically. So all of the x values are staying the same, but the y values are getting multiplied by whatever that number is. If c is between 0 and 1, so some kind of a fractional value that's less than 1, then the graph of y equals c of x is the graph of y equals f of x vertically shrunk by multiplying each of its y coordinates by c. So either way, we're just multiplying the y coordinates of each point by whatever that c value is. If that c value is bigger than 1, it stretches. If it's smaller than 1, then it shrinks vertically. So for our example, we have our f of x graph here. And this is a piecewise defined function. It's got two pieces. One piece is linear, and the other piece looks like it's probably a square root function. And for our first one, we're going to take that and graph y equals 2f of x. So that means we're going to be taking each of the points on this graph, and we'll keep the x values the same, but we're going to multiply the y value by 2. So I'm going to start with the endpoints. This endpoint over here, it is an open circle. So when I graph this one, it's going to be an open circle again. Its current location is 1, 2, 3, 4, 5, 1, 2. So it's at negative 5, 2. And so when I transform this one by multiplying the y value only by 2, then this new point would be at negative 5, 4. So I'm going to plot that one on my new graph here. 1, 2, 3, 4, 5. 1, 2, 3, 4. Open circle. There we go. Now, because this is a line segment here, I'm just going to go to the other end of it, and then I'll figure out where this point is going to be on my new graph. So again, I'm going to get the coordinates of this point. So 0, 1, 2, 3. So this is 0, negative 3. And again, I'm just going to multiply the y value by 2 on this one. So I keep the x value the same, but the y value gets multiplied by 2. So this new point would be at 0, negative 6. So on my graph here, 0, 1, 2, 3, 4, 5, 6. I kind of have to estimate where it's at because that one's falling off my graph. Then between these 2 points, I'm just going to connect them with a line segment, just like it was on the original graph. Now it does look like this was stretched vertically. This point is up higher and this point is down lower. One thing that's kind of interesting though, is you'll notice it still crosses the x-axis at the exact same location. So wherever it's on the x-axis, on the original one, if you're doing a stretch or a shrink, that point is going to be preserved. Let's do the other half now. So my first point on this one, coordinates are at 0, negative 1. So again, I'm going to keep the x value the same, but I'm multiplying the y value by 2. So that would put this new point at 0, negative 2. And it is an open circle. So 0, negative 2 would be here. I'm going to do the same at the other end of this. So the coordinates of this point, 1, 2, 3, 4. That's 4, 1. And so I keep the x value the same, but I multiply the y by 2. So the new point for this one would be at 4, 2. So 1, 2, 3, 4, 1, 2. Here we go. And like I mentioned a minute ago, wherever it crosses the x-axis is going to be a point that stays, even if you're stretching or compressing vertically. So I'm going to go ahead and take the x-intercept from this one and put that on this graph as well to give me an extra point to kind of go through since this one is curved. And then I'll connect them using the same shape. Not really a great picture, but anyway. It does look like this one was taken and stretched vertically. So it's like we grabbed the graph from the top and the bottom and we pulled it apart. Now for our second example there, we're taking the same parent function, our same f of x there, but this time we're going to be graphing y equals 1/3 f of x. So our c value is still positive, but now it is between 0 and 1. But the process is the same. So we're going to take each of these y values from the original function, and we're going to multiply them by 1/3. So on this first point, negative 5, 2, multiplying the y only by 1/3, so 2 times 1/3 is 2/3. So this new point would be at negative 5, 2/3. 1, 2, 3, 4, 5, and then 2/3. Starting right there. Next point was at 0, negative 3. So I'm taking the y value only and multiplying it by 1/3. So a negative 3 times 1/3 is a negative 1. So this point would be at 0, negative 1. And then those two are connected with a line segment. My next point on the original function is at 0, negative 1. So I'm taking the y value from that one and multiplying it by 1/3. So that would put it at 0, negative 1/3. So an open circle here just below the x-axis. The other endpoint on this one was at 4, 1. So multiplying just the y value by 1/3 would give me 4, 1/3. So 1, 2, 3, 4, 1/3 would be right here, just a little bit above the x-axis. And then once again, since this one is curved a little bit, I want to use the x-intercept of this one to help me get the same, help me get the curve a little bit better here. Now this one, since it's being shrunk vertically, it's going to kind of flatten that curve out a little bit, but it should still look a little bit like a curve. That's not really a great picture. It's really hard to draw on here. Okay, our next type of transformation is horizontal stretching and shrinking. So this time we're looking at grabbing the graph from the left side and the right side and either squishing it together or pulling it apart. And much like your horizontal translations, this one is kind of backwards from how you might expect it to be. So for this one, if your c value is greater than 1, then the graph of y equals f of cx is the graph of y equals f of x horizontally shrunk. So if c is greater than 1, it actually shrinks it horizontally. And you find that by dividing each of its x coordinates by whatever c is. So if c is greater than 1, we're going to divide each of the x coordinates by c. The graph on the left shows us this one. So if c is greater than 1, we're shrinking it horizontally. So our original graph is the blue one, and our transformed graph is the pink one. If c is between 0 and 1, then the graph of y equals f of cx is the graph of y equals f of x horizontally stretched by dividing each of its x coordinates by c. So still, we're dividing each of the x coordinates by c, but this time c was something between 0 and 1. So that's in effect going to make the x values larger. So we have a picture of that one over here. Again, our f of x is the blue graph, and our f of cx is the pink graph here. So it is, it's like we grabbed it from the right side and the left side over here, and we pulled it apart to make that new graph. Okay, so again, I'm using the same function that we had before. And this time we're going to be doing horizontal stretches and compressions. And I know that it's horizontal this time because the number that is included in my function notation here is with the x. It's inside the parentheses where the x is. So once again, I do need coordinates from my original function. I think I'm on a different color now. So this one was at negative 5, 2. And this one was at 0, negative 3. This one was at 0, negative 1. And this one was at 4, 1. Okay, so for this one, because the C value is between 0 and 1, this one is going to be a horizontal stretch. So this is going to be stretching it. I take each of the x values from my original function and I divide them by 1/2. Well, dividing by 1/2 is the same as multiplying by 2. So really, I can just multiply each of my x's by 2 on my original function. So for this first one, the x value is -5. So if I multiply that by 2, that would be -10. And the y value stays the same. So my new point would be at -10, 2. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to have to estimate because it fell off the graph. And it was supposed to be an open circle. There we go. When I go to the other end of this, this line segment, the x value on that point is 0. So when I multiply that x value by 2, it's still 0. So I have still 0, -3, which is here, solid point. And then those two are connected with a line segment. Now let's have a look at the x-intercept here because this is interesting. The x-intercept on this one was at -3. On this one, 1, 2, 3, 4, should have been at -6. So my line segment was not perfect, but it should multiply the x value of that by 2 also. Okay, now for the other side here, so 0, -1, the x value being multiplied by 2 and the y value staying the same would actually keep that point right where it's at. The other end was at 4, 1. So if I multiply the x value by 2, that would give me 8, 1. Let's see if I can get there. So 1, 2, 3, 4, 5, 6, 7, 8, 1. Okay, good. That one makes it on the graph here. And then to give me something else to aim for, I'm going to go ahead and use the x-intercept on this one also. So the x-intercept's at 1, 0. So the x-intercept on one that is stretched by a factor of 2 horizontally would be a 2, 0 here. And so I'll connect these with a little bit of a curve so it matches the original function there. Okay, the last one, oops, this is wrong. I'll fix that on yours before I publish it, but this should have been y equals f of 2x. So this one is going to be shrunk horizontally. So to get my new points for this one, I'm going to take the x values from the original function and divide them by 2. So for my first point, -5, 2, the x value is -5. So when I divide that by 2, I'd get -2.5, 2. And so I'd have an open circle there. My y-intercept here, 0, -3. When I multiply its x value by, divide its x value by 2, I get still 0, -3. So 0, -3 is still a point there. This time, let me go ahead and get the x-intercept and divide its x value by 2 also. So that would put an x-intercept at -1.5. I think that'll help me get a better picture here. So now I can connect those dots. And I'll go to the other one. So 0, -1, take its x value and divide by 2, and I still get 0, -1. So open circle here. For the other end, 4, 1. So 4, 1, take its x value, divide by 2, I get 2, 1. And then I'll do the x-intercept on this one also just to get a better picture again. So 0, 1, 0, multiply its x value by, divide its x value by 2. So that would be 1/2, 0. And then I'll connect those. So this one looks like it was shrunk horizontally, compressed from the sides.